Time for our last example in section 8.1. We see that in the United States, the year each coin was minted is printed on the coin. To find the age of a coin, simply subtract the current year from the year printed on the coin. So the ages of circulating pennies are right skewed, which means they make this kind of shape right here. Assume the ages of circulating pennies have a mean of 12.2 years and a standard deviation of 9.9 years. Based on the information given, can we determine the probability that a randomly selected penny, well, that's important, a randomly selected penny is over 16 years old? Well, the answer is no. We cannot calculate this probability because our sample size is n equals 1, which is less than 30, and we know that the distribution is skewed right, the population distribution of the ages of all pennies is skewed right. So since that population distribution is skewed right, we can't find this. Now, if n was greater than 30, then we'd be okay. So make a note. Note, if n was greater than 30, greater than or equal to 30, then that would be fine. Then we would be able to find that probability. Okay. All right, speaking of which, let's let n be greater than 30, shall we? All right, because obviously this is kind of boring if we can't do anything. So, well, at least it's boring for me. So what is the probability that a randomly selected sample of 40 circulating pennies has a mean age greater than 16 years? And we're going to show all the works here. All right, so I'm going to throw in those instructions right there. Now, in order to make this work, we're going to need to figure out a few things about the distribution first. So we're going to have to do that first. So let's figure out this distribution over here on the side. Okay, the distribution is normally distributed, right? So we better make a shape center spread argument. So the shape is normal, which is good. It better be, because otherwise we're not in this course, right? This course is all about normally distributed things, right? So because n equals 40 is greater than 30, so we're good, okay? Then the center is at the mean of the x bars. So that would be where the mean was, which was 12.2. If you remember back here, it said the mean is 12.2. See that right there? Mean is 12.2. Standard deviation is 9.9. See that? We're going to need those two pieces of information here. Oop, there's the mean part right here. Okay, so the mean is 12.2. Then the spread is sigma sub x bar. Copy, paste, there we go. Sigma sub x bar, which is the sigma over the square root of n. So that would be, what was that standard deviation? 9.9. So 9.9 divided by the square root of 40. And that would be approximately, let's see here, 9.9 divided by the square root of 40 is 1.5653. All right, so now that we know those pieces of information, we'll be able to draw a curve and figure out the probability. And of course, a probability would be calculated with a normal CDF. So let me draw a picture and calculate that probability. 1 second. There we go. Now we have a picture. So we can see here's 16, and I want greater than 16, right here. So I put down 16 and I shade to the right. That area over there is what I'm looking for. But of course the area is the probability, and to find that, we'll find normal CDF okay, from what to what? We want 16 comma 1 E99 comma 10 or 12.2 comma 1.5653. I ran out of space there. There we go. All right, so let's find what that is. So I'm going to grab the calculator, clear this out. So distribution, normal CDF. So it was 16, then 1E99. So 1 second comma 99, 12.2, and then our sigma was 9.9 divided by the square root of what would be, how big was our sample? Hold on. It was 40. So I'm going to actually just type that in. That'll be more accurate. All right, then I'll go down to paste and press enter, and I get 0.0076. So let me put that in right here. Okay, beautiful. So we've got that now. Wonderful. Very, very unusual, right? So we can make a note right here. Note, this would be very unusual as the probability is far less than 5%. Okay. All right, now suppose you do get a batch of 40 pennies that has a mean age greater than 16 years. What are some possible conclusions you could reach? So you're going to reach into somebody's purse, bag, whatever. They give their consent, so don't worry about that. So you reach into their bag of 40 pennies and you pull them out, you find their age, and they find that the average age for the 40 pennies in the bag is greater than 16 years. What are some possible reasons that could be happening? All right, let's start with two of the more obvious things. So, for example, start with a bias sample. Perhaps the sample was not truly random. Maybe you happened to select pennies from in a non-random way, or from a penny collector or something like that. Perhaps they knew you were going to collect that day, so they purposely brought the old pennies. Perhaps the person purposefully brought old pennies just to mess you up for whatever reason. All right, that's possible, but in general, we assume that that's not the case. I mean, we assume that we're doing a random sample. So the sample was not, I guess random isn't the best word. I mean, it's not truly representative, right? So maybe you had selected the pennies non-random way or from a penny collector. Perhaps the person brought in a bunch of old pennies because they knew what you were going to do because they're just going to mess with you. Or maybe it just happened. Maybe by sample had a high average just by random chance. Now keep in mind the probability of this is what you found in part B. The probability of this happening is 0.0076, which is very low. But it could happen, right? But it could happen. It's just very unlikely. All right, so now I'm going to kind of lead you a little bit. I'm leading you down a primrose path towards chapter 9 and 10 here, which is, okay, look, if we assume we have a random sample, which we generally do. Now, whether that's a fair assumption to make or not, you know, probably not in a lot of cases, but we're going to go with it. And we're also going to say, look, that chance of that fluke is so low, I think it's something else. So what else could it be? And the only other answer is that all of this is predicated on this being your center and this being your spread, and this being your shape for that matter. What if that's not true? In particular, what if the center and spread are not what you thought they were? What if the Mint, the US Mint, has changed what they're doing, and now the old data of 12.2 and 9.9 is no longer valid? This is how you can start proving that that's the case. So that's your parameters are no longer true. Or perhaps they never were. Haha. So the parameters, what are the parameters? The parameters are mu and sigma, right? Mu and sigma are no longer what they once were. Perhaps they never were those values. We don't even know that, right? So the Mint, perhaps, here, let me put, perhaps the US Mint has changed their coin practices. Maybe they're grabbing them later times or whatever. Perhaps the parameters were never those values, because those values were probably, perhaps the parameters were never those values. Those parameters came from other data sets, so other examples, other samples. So perhaps they were never what we thought they were. Maybe the US Mint was wrong this entire time. This is how you can start proving that those numbers that the US Mint put out are not correct, which go ahead and try it. But generally the US Mint is pretty good about this kind of thing, but people run into this all the time where somebody, some big corporation was saying one thing and it was actually something else. And this is how you can start to prove it, that the numbers that they're claiming are the population values are not true. So the numbers claimed as the population values, that's what parameters are, right? Mu and sigma are no longer true and perhaps never were, right? And this is how you can start proving that. And that's what chapters 10 and 11 and 12 and beyond would all be about. I want to take a moment here to discuss the decision matrix, which I'm actually going to put at the end of these notes in chapter 8, actually probably at the end of 8.1, so you can see whether you should use normal CDF or inverse norm here. So let me just look at this. Now, if you already know, let's think, if you already know your X bar and you are looking for probability, area, proportion, percentile rank, you are going to use normal CDF. Left to right mu with sigma over the square root of n. Now, where have we seen that? Let me go back and look at this problem right here. We knew the X bar was 16, right? They're talking about a mean age. See that word, mean? They're talking about a mean, so therefore this is a X bar. So we're given the X bar and we're looking for the probability. See it right there? So if you're looking for probability and you know your mean, then you're going to be using, according to that decision matrix, you know your X bar and you are looking for probability, you want to find probability, you're going to be using normal CDF. All right, what about back here on this one? It says, what is the first quartile of the sample mean of 15 random students of GRE scores? So this one's a little bit hidden, but you can see that you're given the first quartile and you're looking for a sample mean, right? So you're looking for this guy right here. All right, so if that's the case, go back to the matrix and kind of look it over. You're given, you already know the percent, right? You know that the percent below you is 25. And you're looking for the percentile, if you will. You say, look, I want the 25th percentile. I want the first quartile, right? Those are the same thing. Then you're going to be using inverse norm, right? So it's a little bit tricky because you're looking for a sample mean, kind of, but you're also looking for that first quartile, but the first quartile is given. And that's what makes quartile ones a little bit tricky to you. So that first quartile is that 25th percentile. So you know that that's the area. So you know the area is 0.25 and you're looking for that score, that cutoff, that value, which means you're looking for the sample mean, which means you're going to use this value right here. So you're looking for X bar. You want to find X bar. You want to find that percentile. You're going to use inverse norm. And don't get confused with percentile rank. Percentile rank would be I gave you the X bar. I say, the sample mean is 16. What's the percentile rank of that? That's a different question. But if you're looking for the percentile, which you are in this case, because a quartile is a glorified percentile, then that's this one. Matter of fact, I'll throw quartile in here. Here we go. And we're done with section 8.1.